ideally, one would take the time to do a detailed verification, and I show you how to do that in the laminar pipe flow module. Here, in the interest of time, we'll skip that. I'll show you a couple of checks we can do on overall energy conservation to make sure that the Fluent solver is indeed conserving energy. I can go to Fluent, and under reports, I can say, I can select fluxes. So if I double click on it, I can check the mass flow rate balance, and I show you how to do that in the laminar pipe flow module. So you should do that. And then we can also check the energy balance by selecting the total heat transfer rate option. And I will select all my boundaries, and I will say compute. Okay. So for instance, in the, there's no energy being added in the unheated part of the wall. In the heated part of the wall, you have this many watts being added. And we know the heat flux, right, at that wall, and if you multiply it by the area, we should get that value, and I did double check that. Similarly, that's an input, and one can double check that that's right. And that's also a check on our geometry dimension and our material properties that we put into the solver. And it looks like this overall energy balance, that's good. And the other way, another way we can check the energy balance is to go back to this plot that should look familiar from a previous video. And if, this particular line comes from energy conservation, it's a hand calc. So I could pick, some location, let's say at the axial location of 14 meters, and I can do an integration of the temperature profile at that location and make sure that that value from that integral matches the hand calculation. And the integral comes from the definition of the mixed mean. So this is the definition of the mixed mean temperature, and there's a little bit of confusion in the notation here. So, I was calling this V sub R, or V sub Z rather. In this case, it's called U. So sorry about that. And so this is the mixed mean temperature. And if you look at the right-hand side, ignore U for now, okay? This is the integral of the temperature at some radial, over some cross-section at some given radial location, let's say over here. So if you integrate the temperature over the cross-section and divide it by, I'll ignore U here, and divide it by the area of the cross-section, you just get the average temperature. So that would be the average temperature, but here you also have this multiplication by the velocity, which you can think of as weighting by the velocity. So it's an average that's weighted by the velocity. So let's implement that integral in CFD post, which is one of the neat features in CFD post. So let me get CFD post here. And I will go into the expressions tab, and I'll right click anywhere and say new expression, and I will call it TM, and I can say, okay, I'll give it some name, EXP for expression. I need to do this integral at some radial location, so actually I needed to create a line, radial line, so I'll go to location, line, and I'll say radial line at 14.0 and 14.06, and I'll say 200 samples along that line and apply, and I can go to the wireframe. So if I zoom to fit and I zoom in here, you see that's a location. So essentially I want to do the integral. I want to look along Z here. Essentially I want to do that integral along that radial line. You get the idea. So I'll go back to expression, and I'm still doing TM expression. So to do the integral, I would say variable function CFD post length integral. Okay, so that's that. So that's going to integrate along that radial line, and this is the axial velocity, so I can just right click and say variables. That's the axial velocity, okay? And then you have temperature, so star, I'll say variables, temperature, and then I have 2 pi r, and pi cancels out of the left and right, so I just need 2 times r. So 2 times r is, again, it's, remember the that's what Fluent calls the radial coordinate. Okay, so that's the right hand side except for pi, and then I want to do that integral along radial line. Okay, so that's really the implementation of the right hand side. And then the left hand side, I have to divide it by the left hand side except for Tm, and essentially that is this puppy here, okay, without the temperature. So I'm doing a little bit of cheating here. Okay, so that gives me the mixed mean temperature. That's implemented that integral. And if I go to this plot here, okay, and I look, let me expand this, that's around 383. So my eyeballing it, you know, it seems like that value is plausible. So you can see how you can quickly integrate over a line and check the energy conservation. So that's a check on the energy conservation, and you can use this to calculate the Nusselt number and so on.